one of the things that I really liked about this year's field day, because I'm interested in what are called emergent processes or self-organizing processes, and this field day, I saw about 15 people out there working their butts off, making things happen, and it all came together spontaneously when people wanted to put in effort, and I was absolutely thrilled to see that kind of initiative. I really like, because I've seen things, we've done it before, where just one or two people just practically kill themselves to make it happen. It didn't work that way this time, and it was just wonderful.
Yeah, good morning, everybody. Hopefully this presentation will do a little bit of justice to the topic of antenna modeling. I'll have to preface this with saying that myself, Jeremy, and Craig, when we set this design up, none of us had any experience with antenna modeling. Personally, I have not had any experience with antennas at all in regards to design. So the opportunity came up to get involved in this, and I thought, well, let's just dive into it head first and see what we can learn. So, what happened to our screen there? So I know some of you in the club here have quite a bit of experience modeling antennas. So if I get off the rails here on a particular topic, or I don't say something quite right, then please correct me. But what I'd like to cover with you today is why do we model antennas in the first place, and some of the software tools that we use to model the designs of these things and the characteristics of antennas, and what makes up a model. What's the composition of the model that you have to factor into a design. And then I'm going to show an example, which happens to be the 160-meter delta loop that we stood up on field day, and then any questions and hopefully some answers. So that's the program for the modeling aspect of this. When I'm done with my piece, Jeremy's going to get up and talk about the actual implementation of the design and some of the challenges we face there and performance of that. So why model antennas? This isn't an exhaustive list, but some of the highlights here is you want to assess what the characteristics and the behavior and the efficiency of the antenna design for any given antenna design, whether you're going to put up a dipole or you're going to put up a delta loop or what have you. You also, if you have an existing antenna system, another reason for modeling is to, if you want to make changes to that system, what are those changes? How are they going to impact the performance of that design? And then if you were going to buy an antenna system off the shelf, you may want to look at compare similar designs from different manufacturers, and you may want to model those yourself or look at the models and compare the performance. So those are some of the reasons we model antennas. Some of the software tools out there, you'll find some freebies that help us input the characteristics of a particular antenna design we'd like to build. And so a lot of the software out there is based on some calculation and some analysis engines that are called the numerical electromagnetics code, NEC for short. And these engines, there's different versions of them. NEC 2 is the one I happen to use for this design exercise. There's others out there, NEC 3, NEC 4, and they're all based on the whole NEC model is based on the moments of method calculation algorithms. That comes from the statistics area. So the NEC models embody those algorithms in its calculations and analysis, and produces some results for you. The NEC 2 calculation engines in the public domain, you don't need a license for any software that uses that engine. It does have some limitations. It can't model buried radials or ground stakes. So different tools have different capabilities and may have some restrictions associated with them. The NEC 4 model, it's better, it was rewritten. The NEC 2 engine was rewritten. NEC 2 was written in Fortran, I think, back in the 90s or maybe the 70s. It's been around a long, long time. And so over the years, someone came along and wrote the NEC 4 engine. It's written in C++, I believe. And so but it's more, people find more success with it in modeling smaller antennas. So some examples of applications you'll find out there to model these designs. For NEC 2, it's a freebie. The one I happen to use for the 160 meter delta loop is EasyNEC. There's a demo version, it's a freebie. There's a plus version, version 6 I think is the latest. It comes with a license fee, and the pro version, the plus pro version. There's another application out there, MiniNEC, and another one called MMA and GAL. So I'm going to show you an example of 3 of these later on in the presentation. So what makes up a model? You have inputs. You have to input the characteristics of the antenna, the target design, and it helps to come up with some conceptual model. Draw it out on paper, and get kind of a feel of what it is you want to design and build. And from that, you can then look at what's your target frequency that you're going to design this antenna for, or your frequency band. Is it going to be single band? Is it going to be multi-band? Those will be factors that feed into the model. Wires, elements and segments and connection points. I focused on these because in the 160 meter antenna design, we use the wire element, or we use the wires specification to say how long our wires were going to be and what kind of material they were made of. So wires, segments, the NEC engine, the calculation engine will can automatically segment a wire into smaller portions, and this is how the current is fed through each segment, and hopefully it's uniform end to end as it goes through each segment. The current is, the wave there is going to be uniform across all segments. And then connection points, this is where your wire ends touch one another. So in a delta, you can have 3 connection points there. Sources and loads. Sources is your feed point. That's what the power you're going to feed into the antenna, and any loads out there, whether it's coils or traps or whatever. Ground type is also another factor to be considered. Are you on flat ground? Are you on rocky ground? Is there rock underneath? What composition of the earth and wherever you're going to place the antenna, physically place the antenna, can influence the performance of your design. Transmission lines, transformers, and L networks. You can model those in the software. Wire loss, and I tend to think of this as more like wire type. Is it going to be copper? Is it going to be aluminum or tin or whatever? You can also, there's some capability in there for user-defined wires. System impedance, this usually defaults to 50 ohms, but you can override that and specify your own impedance. So some of the outputs that you get once you've input all the characteristics is things like standing wave ratio plots, elevation and azimuth plots, 3D plots, Smith charts, that kind of stuff to help you assess and analyze the performance. And then optimization. Modeling is very much an iterative process. You put in some parameters, you run the engine and start looking at the outputs and say, well, I need to adjust this or I need to adjust that to see if I can get better performance out of it. So some of the things you try to optimize are minimize the SWR, maximize the gain of the antenna, and try to keep the elevation of the beam within a reasonable range, usually a low angle, because the lower the angle, you can get better skip off the atmosphere. All right. So, frequency. I'm going to dive in just a little bit into some of these topics here. Frequency, you have to know what your target is. That's going to influence the length of your wires, influence a lot of a lot of the physical characteristics of the antenna. Consider if you're going after a frequency band, then consider putting your specification in as the center of that band, the center frequency. And those are going to result in, usually these tools give you, you put in a frequency and it tells you what the wavelength is. So wires and segments. Key component here, you got to have wires or you got to have elements to make an antenna. And a wire's length, like I said, it's modeled as a series of segments, and they have a uniform current value across them. And again, it's based on the method of moment principle. Any of us who've looked at, who studied the extra license, and for the extra license, you'll see some question or two there about method of moments and segments. And those, the segments, the number of segments can be, you can take a default or you can specify your own value for these. And there's some guidelines on how you look at segments in terms of your wire lengths. And those are going to influence the outcome of the analysis and the calculations in terms of currents and impedance. The number of segments per wire, you can, like I said, you can define those yourself. You can override what the software gives you automatically. Connection points, there's a nomenclature in these tools on how you specify connection points. So the example here, I have wire 1, end 2, and that can connect to wire 2, end 1, so that you have a junction, and so on. If you want a connection in the center of a wire, you might say W1C, wire 1 center. So there's a little bit of a convention there that these tools use to specify connection points. Some of the guidelines here, the software tools suggest a minimum of 10 segments per half wavelength for pattern and gain analysis, and to get more accurate or more granular analysis, you can increase that. Some have suggested that you can double that value to get more accurate impedance values. If you go too low, if you go below the minimum, you may not get very good results on the analysis. Sources, like I said, this is the feed point. This is where you apply power to the antenna. Ground type. Ground type is, I've seen 3 options. Free space, so for example, if you're going to send up a balloon, your antenna's on a balloon, you want to transmit telemetry data or photos or video, then you might consider that a free space environment. Real ground is like what we did over the field day. You know, we have actual earth beneath us, and there are some parameters you can feed there on what kind of ground you think you're going to be on. Perfect ground, I haven't found a need for that. I don't know what perfect ground really, how that would apply. Haven't had a need to use it just yet. Wire loss, again, like I said, I see that more as wire type, copper, tin, aluminum, whatever. And then the alternate impedance, you can override what the system gives you. Normally we use 50 ohms impedance for our transmission lines and feeding into our antennas, but you can override that. In our case, with the 160 meter design, we had 200 ohms at the antenna. So some of the outputs you get out of all these characteristics you feed into the software, azimuth and elevation radiation plots. Here's what the pattern is going to look like. Azimuth is basically your horizontal plane. That's what the pattern would look like. Elevation, here's what it's going to look like if it's, vertically, how that pattern's expected to emanate. And this is the projection based on the characteristics you feed to the model.
Was that for the 160?
That did come out.
Back up the slide for just a second. So you're saying that it favors one side or the other of that. Is it broadside of the loop, or is it on the ends of the loop, or what for your azimuth?
The azimuth, this was on the, when I oriented this, I put the y-axis pointing north. So this is the y-axis, positive y, negative y, right? So we were getting a lot of, most of the radiation off the back end of that. And then that's the comparable elevation profile for that same plot. And I think this was on the 80-meter band, actually. The 160-meter plot looked a little less defined. SWR plots and Smith charts. This was, the way you read this is the frequency range. Again, this is the 80 meter, 3.5, that's the bottom end of the 80 meter band, and 4 megahertz up there on the top end. And so our standing wave ratio, starting at 3.5 megahertz, we were a little under 2 here, and it dipped down to about 1.5, and then it just started climbing from there, the higher you got in the band. And that was another reason why we want to put an antenna tuner on that, so we can keep it within a reasonable range and not let the standing wave ratio get too high.
Is that saying the elements were probably too short then to go to the center?
Too long.
Or too long? Too long? Too short? Too long?
Depends on what you want.
What frequency?
It's great for CW.
Yeah,
Excellent for CW.
this was a plot that I believe the sides were about 160 feet. The bottom was about 196 feet. We also added additional length later in the day as we started trying to use the antenna and we put an antenna analyzer on it and looked at it and said, in the real world, because remember this is a model, right? And so your mileage may differ a little bit when you get into the physical world. But yeah, so we put an antenna analyzer on it and said, this doesn't look real great, so let's add some length to this. So this is the drawing that we put together for the delta loop, and the wire for the antenna itself is this triangle right here. It was actual implementation. This bottom wire was 7 feet off the ground, roughly 7 feet off the ground. The sides were 138 feet long, 138 and a half feet long. The bottom 196 feet. We fed in. We had a Ballon, a 4-to-1 Ballon over here at the shack, or actually on the antenna post here. These were support posts, and we had another support post over here to hold the bottom wire in place. And we had a 4-to-1 Ballon here with I think about 100 and 150 feet of transmission line going.
150.
Yeah, going into the van. So that's what it looked like, and initially we thought we were going to put up a weather balloon here, and as you all know, we ended up using multiple party balloons because the weather balloon popped while it was being filled. And actually that turned out to be a positive aspect, an improvement to this design, because now if one balloon popped, you still had others still holding the apex of the antenna up.
Where was your feed point?
Our feed point was in the corner. It was here, and the coax cable from the trailer came from here, and the Ballon was actually mounted right at the corner of the antenna on the post. At this point, I wanted to bring up the model and show you what a model looks like in the EasyNet application, and explain to you a little bit about what it takes to put these characteristics into a software tool. All right, this may be really difficult for everyone to see. I know it's kind of small. The resolution on my laptop there changed when we plugged it into the projector here. But essentially, in this particular tool, you'll see that this area right here in the user interface is all your inputs into the design. The buttons here are going to be the outputs that you want to see from the results of the calculation. So we come in and one of the first things we do is specify the frequency range. And I put the bottom of the 160 meter band here for the frequency. It automatically gave me a wavelength of 546 and some change, 546 feet for a full wavelength. The wires entry here, it says 3 wires, 453 segments. And this is where you specify on an XYZ axis. If our bottom wire is 196 feet, remember Y is pointing north, positive Y is pointing north, negative Y is pointing south, X, left and right, east and west. Z is the elevation. So we put in some parameters here. Minus 98 is this point right here, and that's for wire number 1. Positive 98 is this point up here, and you add those together, it's 196, right? The second wire here was, we started at a positive 98, and we went to 138 feet along the z-axis here, 138.5. One thing I noticed about this, well, let me get to that in a moment. And then the third wire is similar to that. It's 138 feet, starts here, and we go to minus 98 down here. The z-axis says we're 7 feet off the ground, so this bottom wire is 7 feet off the ground here. So these are things you have to think about when you're modeling the wires. One thing I did notice is this 138 feet, and I spotted this the other day actually. It threw the model off a little bit, but 138.5 feet is along this, it's from this origin to here. And so that will make this wire not 138 feet, but I think we saw 164, 169, something, or 160. You don't know what I didn't notice what the wire length was in the model, but the only way I could find out so far that I've been able to find is you have to mouse over the wire and then it shows you the length. It's like, okay. All right, that got me. But when the physical implementation of this model, however, was 138.5 feet on the sides and 196 on the bottom. So by being off in the model, then our plots and our SWR plot, our radiation plots may be a bit off.
Hey, found that extra 100 feet.
Yeah, so when we first tested, and let me add that we didn't have any opportunity to pre-test this design in the physical world. The first time I think any of us saw the equipment was field day. So this was our first and only chance we had to see how this thing behaved. All right, let's look at sources. This is, did that come up? Yeah. Okay. So sources is, you see this, I don't know if any of you can see, there's a little red circle here, and that's where your connection point is for the power you're going to feed into the antenna. So the way you specify that in this particular application, you say wire number 1, it's 100% from end 1. So that's going to put it down here. If you mouse over this, I think this half of the bottom wire shows you end 1, and this shows you end 1. Yeah, right. So wire 1, end 2. That's the other half. Wire 1, 100% from end 1. So at end 2. And the thing about this particular design is you actually have 2 connection points here at this corner. One for one side of the coax and the other one for the other side, or the balun that we put on there. So you specify it as a split connection. That's what the SI means, split current. There's also an option here for split voltage. So that's how you specify sources. Yes, sir.
Tom, this may sound dumb, but was there a reason that you feed it from a corner and not from the center or the bottom?
Yeah, I modeled, I went through many iterations of this model, and I put the connection in the center here, and the plots just, the SWR, I couldn't get it within a reasonable range, at least according to the software. Yeah.
If I'm not mistaken, on a delta loop, that's what this is. If you feed it in a corner, it's going to give you a vertical polarization.
That's right.
If you feed it in the middle, it's going to give you horizontal polarization. With only being 7.5 feet above ground in horizontal polarization, that means you're going to be all kinds of wacky readings as far as your SWR because you're not looking at the antenna as a horizontal at 7.5 feet above ground, but a vertical is that 7.5 feet above ground really doesn't have too much effect on it as long as you have your full loop.
Yeah, you want a low takeoff angle anyway for distance.
Yeah.
Yeah, and I think as you'll see here in a moment, I think we had about 22 degrees on takeoff angle, which isn't great. I would like it lower than that, but
Yeah.
More grounding.
yeah, yeah. So that's sources. I didn't bother with any loads, transmission lines, transfer. I didn't have any specs about the transfer. I didn't know what we were going to use. But so that's why I put the specification in here for the alternate SWR at 200 ohms. That's right at the connection point.
That's about right.
Yeah.
Yeah, another thing, Tom, if you want to get more elaborate, you put 2 of those in there and then you aim it for the southeast or something like that. You'll really get some gain.
The other thing about this is you, when you start putting these parameters in, these coordinates, you also have to make sure that you have the proper unit of measure set. This was feet. Yeah.
Instead of meters.
Instead of meters, yeah. You can do it in meters if you can do the math in your head, but I'm not that great at the metric system. So, and again, the ground type, we put real high accuracy, and then the ground description. These are preset, for the ground we thought we were going to be on. So I didn't really monkey with these. I just said, yeah, give me real ground, and that's what it gave me. All right, so let's look at some of the outputs here. Some of the more interesting ones. This is when you click the view antenna, this is what you get. You get a graphical representation of what the design looks like. SWR sweep, these parameters, you say that what the start frequency is and in the 160 meter band. In order to model what the SWR plot's going to look like, you put the bottom of the band, the top of the band, and this is the frequency step. So it's going to sweep through all those frequencies in that range and give you a graphical plot. So let's go ahead and hit run on that, Phil. So it goes through and does geometry check and calculating impedances, et cetera, and this will run for a few seconds. Okay, so if we want to, so this looks really bad.
Yeah.
And this is because this is the impedance is, automatically defaults to 50 ohms. So Phil on the left side of that.
Put 100 ohms in there.
Yeah. Click Alt 200, and it brings the SWR down. So this is right at the connection point, right, of the antenna, because I didn't model a balun, didn't model any matching coils or anything like that, right? So it starts bringing it down within a reasonable range.
Middle of the band.
What's that? The middle of the band. Yep.
That's great.
Yep. So if you move this, there's a way to move this little dot here, and you can see it'll update this information down here. Right now, there you go. So now we're at 1.9 megahertz, and the standing wave ratio is 1.14 at that frequency. So you can continue to move that little green dot along this line, and you can monitor that to see how to adjust the values. So that's an SWR plot, and for that particular run of the analysis, this is what the Smith chart looks like. I understand this is about impedance matching. I'm still trying to figure out how to read these charts. Anybody know how to read a Smith chart? Good.
There's a section on the test.
Anyway, to let you know, it's available out there if you know how to read it.
He's dead, long time ago.
So what I understand is there's a horizontal line going through this circle. At this point, this is as if the circuit is open. And at this end, it's a short circuit. And so what this thing is trying to do, and one is usually the sweet spot here for the impedance. This is a relative number, and so if when it plots out the impedances, it tries to plot it along these circles, these concentric circles, to tell you how good or how bad the impedance matching is. So this is, again, for this frequency range, this is what the 3D plot looks like of, and get a little bit better idea with this if we present it as 2D. 3D, especially at this resolution of this thing, it's difficult to tell what that pattern really looks like. So Phil, there's a, if you say show 2D plot, there you go. So this is what the elevation pattern looks like. So we have a 2D elevation plot, and this is what that pattern looks like when we've run the analysis. This, again, yeah, and that's the azimuth plot for 160 meters. It almost looks like a perfect circle.
Nice.
Yeah. So here, we have that little green dot again. You can move it around this pattern and look at the changes of the elevation angle and bearing and the gain and all that the other information, the supporting information down there about that particular plot.
It does it on the 3D too.
Mm-hmm. Yeah.
Oh, yeah, you see the green dots spinning around there.
Yeah. All right, so we saw elevation, azimuth slice is basically the same thing, except it's a horizontal plane.
Yeah, very good.